With 2 limitations, there's 4 real things that you have to know, but 2 are really what I consider limitations. The 4th is just a rearrangement, which is not necessarily a limitation, it's just something to be aware of. Again, our Friedel-Crafts alkylation, we add a carbocation. Because of the need to add this carbocation, you need to have things that can form carbocation. So our first limitation is one in which we are we can't generate certain types of cations, like sp2 and sp hybridized carbons. Second of all, another limitation that we have is there are certain substituents that react in our flask. So for instance, aluminum chloride or Lewis acids can react with some of our substituents on the ring, as well as some of our substituents in the ring help to slow down the alkylation reaction. And our third limitation is the fact that once you add one alkyl group, it makes it easy to do polyalkylation at that point. So what we're going to, and then lastly again, rearrangement is something, anytime we see carbocations, there's always an issue. It's not necessarily a limitation per se, but it's always something you need to factor in. So for Friedel-Crafts alkylation, it's very important to note that since we're doing alkylation, there's a reason it's called alkylation. It's because only alkylation is going to work. We are not going to be able to form aryl carbocations easily, nor are we going to be able to form vinyl carbocations easily. Because of that, that makes these not very reactive possibilities, because they're not easy to form. Forming carbocations out of sp2 and sp hybridized carbons is almost virtually impossible. I'm not going to say not 100% impossible, but not very possible, because they're not very stable, based on the fact that their hybridization makes that charge close to the nucleus and hence not very stable. So for the purposes of this class, we say that it doesn't happen, but I'm going to stress that it really is, that it's just almost impossible. And we're limited to alkyl groups, and hence the name Friedel-Crafts alkylation. That's why we're going to say that. So the ways that we could add these vinyl groups anyway to aromatic molecules would be things like the Hex, the Suzuki, and the Shinagashira reactions. So those are presented in class, and so those are the places that you will see this. Our next limitation of this reaction has more to do with side reactions that can happen. It's not really the reaction itself, it's just the reagents in the reaction. So for all intents and purposes, you're going to say that there's kind of no reaction, but it will give you some reaction. One of the problems is that aluminum chloride. The second problem is actually the substituent that could be on the ring. So one of the big issues with the substituents, and we'll talk about that when we get to that point, is that the substituents in the ring in this case are called Y. Ones listed here are strongly electron withdrawing groups. And because they're strongly electron withdrawing groups, we see for this first major factor that these strong electron withdrawing groups, and sorry, the little things in the brackets at the bottom are not electron withdrawing groups, but everything else above it is. These strong electron withdrawing groups make your reaction harder to happen, and because they're harder to happen, you don't get much alkylation. Alkylation is already difficult as it is, and so these strong electron withdrawing groups lessen the reaction's ability to happen, and so we don't get very much product. So later on we'll talk about that electron withdrawing groups slow down the reaction. The word for it is deactivate. And so very often you're not going to get a usable reaction. Our second category has to do with the things at the bottom. These are not electron withdrawing groups, by the way, but they are amino groups, and amino groups are bases. So if we have an acid, the amino group being a Lewis base will react with the Lewis acid and make it so that we take the Lewis acid out of the reaction. And by doing that, this then limits the possibility of this reaction. What will happen is the amino group will donate a lone pair into the MTP orbital of the Lewis acid, and then we have a reaction that doesn't complete because the Lewis acid is not there anymore. So now we no longer have a Lewis acid. Our next category is more of what we call a control problem, and we'll go into more of this in the next video and more in class. polyalkylation is possible in these reactions, and polyalkylation means that once we add one alkyl group, it makes it much easier to add more alkyl groups because we've made the ring more reactive, or what we say, we activate the ring. And so by addition of the alkyl groups, you're going to have more alkyl groups. You're going to allow more alkyl groups to be added onto your ring. Our second issue is rearrangement when we're associated with control problems. This is really not, it is an issue, but it's something that we've already experienced before, so it's not really a new thing for us. It is more of the fact that whenever you see a carbocation, think of rearrangement. By making the ring, you're going to make it easier for each subsequent addition to happen. Acylation is the same idea. So you take the aluminum trichloride, the lone pairs on the chlorine will attack. You get this molecule, which is very unstable, and so this will split apart. And so in the past, we've talked about you can't make a cation on a carbonyl. So this is very reactive. There is some resonance stabilization that can happen in this process, but this cation, being very reactive, will then undergo electrophilic aromatic substitution, just like what we saw before. And again, we repeat the same process. So it attacks the carbonyl, this comes up. So this is resonance stabilized, so in essence that can go back down. So you would take your base again, if you start with phenol, in the presence of sodium hydroxide, CO2, and then heat, and in the second step, acid, we can make a carboxylic acid in the position, the ortho position to the phenol. So it's actually a very similar mechanism, except it uses the phenol as a part of the mechanism to help to stabilize your intermediates. And so the first thing is, in basic conditions, we take the phenol, deprotonate it to phenoxide. Beg the question, why sodium hydroxide, why not other things? I mentioned this in class, but we'll talk about this in a second. So you get phenoxide ion, and with the phenoxide ion, that can undergo resonance, putting a negative charge next to the phenol. You can also get, by resonance, a negative charge here, but there's a reason you don't really form the product on that side. So your CO2 being partially positive in the middle, kind of like when we did this with Grignards, this will come down. You get your carboxylate ion. And this is not terribly stable, and your molecule wants to reattain aromaticity. And so in this process, we're going to end up protonating, but before that happens, I'm just going to draw this the other way. Essentially, we do the same kind of idea that we saw before, and we can use our water that we generated earlier to deprotonate that hydrogen and reattain aromaticity. So we have our phenoxide, we have our carboxylate ion, and in the presence of the acid, you protonate both. So we've drawn protonation steps numerous times, but basically you're going to protonate with the acid in step 2, and then also protonate here, and you get this. Now, one of the driving forces to keep this reaction ortho is that the sodium actually in this mechanism plays a role of being between the carbonyl and the CO2 and kind of anchors the two together. So in the end, you're kind of anchoring the CO2, and that makes them have to be close to each other. So if they're in the 1 and the 4 position, that doesn't really happen. Like aromatic substitution. And then when we were in Unit 3, when we were in Chapter 23, we talked about this reaction, but I said I would come back to it because we hadn't learned anything about it yet. So these diazonium salts can be attacked also by aromatic rings because this is a great electrophile. And so your aromatic ring attacks the diazonium salt, and we get these azo compounds. And these azo compounds I mentioned before are what we're using to form these different colors. So the step that's missing in between is that we get the phenol in this case, and we'll talk about why things attack from what position later on. But you add the diazonium salt, you have your hydrogen, you have your plus charge, and then you can use any trace of water or anything like that in your mechanism. Any sort of base. Now, this is not a base. In your textbook, they use it as a base. That is wrong. That's an error in your textbook. Chloride ion is not a base. So it's your water that will come in, deprotonate that hydrogen, and then reform that aromatic molecule. So our next step after this is that we will move into ways of adding things onto your aromatic ring. But there's one mechanism that is not in your textbook, and it's to make your OH cation. So you're going to take hydrogen peroxide, and you're going to take something called hydrofluorosulfonic acid. And this is a superacid, so it's stronger than sulfuric acid, and but strong enough to deprotonate something that is a very mild, very, very mild base. The thing is so strong that it can eat through various types of glass, so you have to use very special glassware to do this. And so in this case, it's a strong acid. We'll deprotonate that acid because it's so strong that even hydrogen peroxide can do that. We get this cation, this hydronium ion, which is going to leave as a leaving group. And we get HO plus water. And so we can do our mechanism. So your textbook has some other ways of adding OH, and it's not in your textbook. So the water is the base, and so it's actually acid catalyzed again, and you get phenol out of this reaction. So in class we'll talk more about the electrophilic aromatic substitution, and next week's videos will go into where things are on the ring and how it influences the reaction.